10.4 Simple Pendulum. So I really like this chapter because it's hard in the book because they don't explain the derivations, and they only expect you to know equivalent forms. They kind of do the same thing with rotational energy, but the actual proof for rotational energy requires not binomial expansion theorem, but a binomial expansion. And fortunately, 10.4 is simple algebra, and I have the proofs, and the book doesn't explain them, so I'm going to do so here. So what is a pendulum? All it is just a point mass connected to a massless strings, swinging under gravity. So I don't have any pictures here, but I think I can draw one. So it would just essentially be the axis here, which is just assume everything is massless, but the weight at the bob of the pendulum, which we'll get to a little bit later, and that's a mass, and it's swinging back and forth through gravity. But obviously, the center of gravity or the center of mass, same thing here. Actually, wouldn't really be the same thing because gravity acts differently. Actually, it's a point mass, so yes, the center of gravity and center of mass are the same. But this is a simple pendulum, so nothing will ever exist like this in reality. So when we use pendulums in real life, there's a lot of applications to pendulums. First, we have the grandfather clock, um, and I have a few examples in my head, but I'm not going to share them. So if you just leave this on a string, it's just going to stay there. But what happens if I push this, kind of like how you push a spring, such that the mass goes this way? What happens is now there's a force acting on this, which again will correspond with the lever arm. So we're going to learn a little bit about that. But this is essentially what a pendulum is. I'm sure you've made something like a pendulum. Um, so if you have a string and you attach it to a block or something like that, um, then that will be a simple pendulum. But the thing about simple pendulums is we assume gravity is the only force acting. But in real life, you have um, drag, heat, friction, air resistance. Well, air resistance is drag, so here we're just going to assume gravity is the only one acting. But obviously, with ideal and real life applications, they tend to be quite similar. Like the margin of error only tends to be 5% because non conservative forces aren't really that dangerous within classical mechanics. So it follows simple harmonic motion. So we've learned before that simple harmonic motion is negative AW squared cosine WT, or it takes the form negative position times W squared, or the other, or negative W squared X. So the interesting thing about that is I can derive it for you, but I've already done so in chapter 10.2. So I'm not going to do so. But essentially, everything with a period follows this form. So it would be the squared angular velocity times the position, and a negative, just because this will always act opposite to the displacement. So if we assume the axis is, and we'll get to a little bit later, but if you assume, like, for example, if we take a spring and we denote this as the initial position, if it goes this way, it's a plus displacement and a minus displacement. So if you plug that plus displacement into here, you get a negative total acceleration, which acts opposite to that positive thing. And if you plug the negative one here, you get a positive squared angular velocity times the position, which is accurate because, again, it acts different to the negative displacement. So that's really interesting. So I'm going to go over the proofs because the book doesn't do so. The book just says here, just kind of understand it how it is. But I'll just explain the full algebraic proof. So before we do so, I just want to say that this is actually pretty interesting because we use something called small angle approximation. So let's redraw that pendulum picture here. And let's do this here. So remember, gravity only acts downwards. Now, this is going to be, for most part, it doesn't only act downwards relative to an axis, though. So remember, as we said, if we push the pendulum like right here, now we've given it gravitational potential energy due to the change of height. So if the gravity is acting this way, then now we have a torque because the lever arm would be the x component of this distance times the force, as we learned before. So what's interesting is that we can do that torque is equal to the force um, times the lever arm. So we'll just denote this as some arbitrary distance L. Um, and if you want to use classical logic here and assume theta, then this side would be considered L sine theta. So that is essentially the torque formula because that's the lever arm. But the interesting thing here is that we also have to say negative because it acts opposite to the displacement. Or you can just denote gravity as negative, which works as well. So it would, but people usually say G is 9.81, not negative 9.81. So it would be negative mg L sine theta. Now, and also since we did negative on the acceleration formula with the omega and angular velocity, they will cancel out, which is quite interesting when we get to square roots and stuff, because math always seems to figure itself out in the end. So something about sine theta is really interesting, and if you've taken calculus, I'm sure you know that sine theta of small angles is equal to theta. And I guess I could prove it a bunch of different ways, but I'm not going to do so. Like you can probably prove it with Pythagorean theorem that the as x squared becomes really low, the square roots of the hypotenuse squared minus the adjacent side squared will essentially just be the opposite, which is going to be equal to that theta. So that's really interesting there. So what we're going to do is, if we know that this is the torque, what did we know before? Well, we knew that torque is equal to another form of torque, which is called the moment of inertia times angular acceleration. But we also know something else. Well, first let's solve for the angular acceleration, because that's what we're trying to find here with that torque. So what we're going to do is we're going to rearrange this algebraically, and this is just simple algebra. You just divide I on both sides, such that you get the form negative mgl sine theta I. So you can use this formula. This works too, but physicists like to simplify these formulas. So what did we know about this? Well, we knew it was a point mass. So we're not going to be dealing with any 3D volumetric shapes here. So we're not going to be dealing with 2/5 mr squared for a sphere. We're not going to be dealing with 1/2 mr squared for a cylinder. We're just going to be dealing with a point mass, which is mr squared, which simplifies things a lot. Hence the name simple pendulum. And we have the negative mgl sine theta. Since r is equivalent to L, because at the lowest point of the pendulum, or at theta equals 0 degrees, L equals r. So now, or it's always an L distance away. That's what a pendulum is. So now what we can do is we can cross out some algebraic terms. Also, sine theta should just be theta because of small angle approximation, as we mentioned before. So now we get negative g theta over L. So this is the form that we have here, and we're going to go back over here. So now let's go back to the slide so I can explain a little bit further. So notice that this entire term is constant. So it kind of looks like the spring formula that we've learned before. F equals negative kx, where k and theta are equivalents because, or x and theta are equivalents because x is displacement, theta is not displacement, or theta is angular displacement. So essentially two terms here. So that's how the book kind of likes to derive it, but I don't like it that way because I'm not going to just accept something because it sounds sound. I'm going to attempt to prove it algebraically. So torque equals force times lever arm. So this is the entire proof. So we come over here, and now what we're going to do is we're going to set angular acceleration equal to a certain variable. So we know here that angular acceleration is negative mgl over I. But we also know, looking here, oh yeah, that's pretty stupid. That sine theta is essentially equal to theta. So we get the form negative g theta over L is equal to, it would be negative g theta over L. That would be equal to negative w squared theta. And you can cross out theta on both sides, and the negative you can times on both sides. So the reason we use this formula is, again, that was the formula for any simple harmonic motion, except this time we're dealing with angular velocity, or we're dealing with a period which appears in the pendulum because a period would be back and forth, and this is simple harmonic motion once again. So the formula becomes W equals square root G divided by L. Now we notice something interesting here, and we notice that there is no mass in this equation. What does that mean? That means the weight at the bob of any pendulum has no effect on swing speed. Yeah, which is quite interesting because you would think that maybe a heavier object would be a little bit slower in terms of its periodic motion, but it's not. So inertia cancels out accordingly here, which is pretty interesting. So I mean, it probably wouldn't work in real life because there's more friction on higher volume surfaces, stuff like that. Like you can't do a feather and a brick. The brick will have a faster angular velocity. But if you did try like a brick and a truck, they would be swinging at the same exact speed, which is interesting. So, of course, this is something else. But here's the thing with algebra, you can manipulate this into many different variables. So what is W again? W is equal to 2 pi frequency, or 2 pi over T, which is square root G over L. Guess what we can do? We can multiply or set the power of -1 at both sides. And what happens here, actually this should be square root as well, is it'll flip both sides to get square root L over square root G is equal to T over 2 pi. Multiply 2 pi on both sides to get 2 pi square root L over square root G. So again, just simple, interesting stuff like that. I mean, physics is really interesting, and I love how it's all theoretical, at least for us. So that's all for that. And the further application should be, oh yeah, gravity. So remember that we established W to be square root G over L. Well, that means you can calculate gravity at any planet. Let's square both sides times L equals G. I wonder what they did here. I think they just set W equal to 2 pi over T. Yep. So what they did was they just did 2 pi squared times L equals G. Actually, I forgot the divided by T. And applying this algebraically, you get 4 pi squared L over T squared is equal to G. So let me see if the form is equivalent. And fortunately it is. So you can calculate gravity with any pendulum, which is interesting. So if you're ever on another planet, or if you're at a certain altitude where you want to know what the gravitational force or acceleration would be, just bring a pendulum with you and everything will settle out accordingly. Though it will differ a little bit because of air resistance, and also nothing in this world is really a point mass, because a point has no dimension space or anything of that sort. So really interesting thing here. And I'm going to get to Young's modulus in the next one, which is also really interesting because we learn about tensile strength and strength of materials. So